Go ahead, Bill.
Great, thank you, Lynn. Hello, everyone. Thank you for attending today's webcast. This is session 9, Energy Star Water Heater Specification and Test Method for Connected Water Heaters. I'm Bill Hoskin, National Utility Program Manager at A.O. Smith and the moderator of this session. Before we get started with the webcast, we have a few housekeeping announcements, and then we'll quickly move on to our speakers, followed by a short Q&A, provided we have time. As a reminder, your screen is customizable, utilizing the various widgets found at the bottom of your screen. Presentations can be downloaded as PDFs from the resource list in the menu. Attendees are in listen-only mode, but can submit questions through the Q&A box anytime during the webcast. Presenters will be answering questions following the presentations, time allowing. All presentations will be available for on-demand viewing within a few days of the webcast. Discussion rooms will open at the end of the webcast to continue the conversations and to allow for additional questions. Just click on the Zoom widget or download the daily link PDF available on the Engagement Hub. Please be sure to complete the form survey after your last webcast. It really helps ACEEE in planning future forums. ACA would appreciate your feedback regarding this year's Hot Water Forum. You'll have access to the survey link and all of this week's sessions on your console. Please take a moment after you watch the last webcast and complete the survey. For those that do, you will receive a $25 discount off of your registration for the 2022 Hot Water Forum in Atlanta, Georgia. Last, we want to thank all of our sponsors and partners for their support of the Hot Water Forum. And I'd like to introduce our distinguished panel of speakers. They are Bethany Sparn, Senior Research Engineer at NREL, Forrest Frizzell, CEO of Shifted Energy, and Kashif Nawaz, Senior Researcher at Oak Ridge National Lab. Today we'll start with our first speaker, who is Bethany Sparn. Bethany joined NREL in 2010 and is a research engineer in a residential building group. Over the course of her career at NREL, she has been involved in numerous projects involving heat pump water heaters. She has conducted detailed performance mapping of heat pump water heaters, evaluated control of heat pump water heaters through standards like CTA 2045, and has ran experiments with heat pump water heaters that were controlled as part of a larger whole home strategy. Today, Bethany will provide a brief overview of the brand new Energy Star water heater specification and test method for connected water heaters. Bethany, it's all yours.
Okay. All right, thanks, Bill. I'm going to be talking today about the new test method that's associated with the updated Energy Star water heater specification. So some of you may be aware that Energy Star has been working on a new version of its product specification for residential water heaters. Among some other updates, this new version also includes a definition for connected water heaters, product criteria, and a test method to validate demand response. DOE is developing the test method, and we're going to be focusing today on what is included in that. We're going to talk about the test method itself, results from a couple of water heaters, and the status of the product specification. We were working on this project to vet the test method. We were going through the process of testing it out with connected water heaters so that we could understand if anything wasn't working quite right or wasn't giving us repeatable results. And we did find a few little small tweaks to make the test method just that much better. But you know, our project and this presentation are really going to be focusing on the test method and not going into results from any of the products, because we are not a ratings lab, and the test method was actually not finalized when we were doing the testing. So. Okay, with that, a big picture overview of the test method. It includes several different tests, but the bulk of the test is this load shift test. And there are two different versions. There's load shift with basic load up, where there's no change in the set point allowed, and then load shift with advanced load up, where a set point increase is allowed during the load up portion. There's a few other shorter tests: consumer override, loss of connectivity, emergency curtailment, and grid emergency. And we will talk about those a little bit later. So the testing that you'll learn about today was done in our systems performance lab, which is shown here. This lab is not designed to do ratings tests, but it does have all the infrastructure that was needed to do this test method validation work. We did make some tweaks to the infrastructure just so that we could match the DOE test procedure a little bit closer. But again, none of the results that, or none of the data that you're going to see is official. We looked at two different connected water heater products. One of them used CTA 2045 for communication, and we did those tests using an EPRI test cable. And then the second unit was Wi-Fi connected, and we used the manufacturer's web portal to send commands. A little bit more on the laboratory infrastructure, just so you can see details of the plumbing. So mains water comes in, and hold on one second. Okay. Yes, let me know if anyone has trouble seeing the slides, but they seem to be fine for me. So mains water is coming in. We did some of these tests last summer, and we found that our mains water in Colorado in the summer was a little warmer than the test method was calling for. So we did use an ice bath to cool it off for the summer tests. And then we have a dump drain here, basically. This lab is within a much larger building, and so there's lots of room temperature water just sitting in the pipes. So we would dump all that room temperature water out to make sure that our inlet temperature was consistent through our tests. Inlet thermocouple, 24 inches above the inlet. This is not a to scale drawing. And then on the outlet side, we had a mixing valve installed because some of the tests had a set point above 125. 125 was our base user set point, and we used a mixing valve to ensure that even if the water heater was set higher, the outlet temperature was still being maintained at 125. Outlet thermocouple, again, 24 inches above, and then we have a series of valves at the end. So a control valve to allow us to change the flow rate, a solenoid valve to ensure that the draws were sort of crisp on and off, and then a flow meter. Not shown in this diagram, but was included in the tests were 6 internal temperature measurements as outlined in the UEF test teacher. Okay, so a lot of words here. We're going to walk through the basic load up test procedure, and then we're going to see some data that I think will make it a little bit clearer as to how this all works. But the load shift test is basically 3 different sections. So there's a normal operation that's a 4-hour period, basic load up with no change in set point, and then a curtailment period, which is another 4-hour window. So before anything starts, the water heater is left idle for 12 hours. And then before beginning the true normal operation, we do a draw to initiate heating. So this is kind of a preheating step. Once that heating is complete, we wait for the water heater to settle. And so the definition of settling is 10 minutes or the time it takes to get to the maximum tank temperature, whichever's longer. And there's definitions of how to figure out that maximum tank temperature in the test procedure. For all of the test data that you'll see here, we used a 10-minute settling time since that was the longer time for us. Okay, so the water heater has been preheated, has had a little time to settle, and then we start the load shift draw pattern, which is defined as the first cluster of draws from the rated draw pattern in the UEF test procedure. So that begins a normal period, and then after 4 hours, we move on to the basic load up portion. If the water heater is not heating at the end of that 4 hours, you start a draw to initiate heating, wait for settling, and then you do a draw that is 2 gallons less than the amount that was triggered heating in the first draw. So this load shift draw pattern starts off with one big draw. So if the water heater starts heating during that one big draw, you have determined the volume to initiate heating that's needed for the basic load up portion. If heating did not start during that first draw, you'll do another big draw during this basic load up portion to figure out the volume of water needed to initiate heating. And then once that heating is complete, then you can move on to this draw that is 2 gallons less than that volume to initiate heating. The intent being we want to draw enough water so that it's not quite heating yet, but that when we send the basic load up command, heating does begin. So we do this big draw, less than 2 gallons less than the one needed to initiate heating, and then we send the basic load up command and heating begins. Once that heating cycle is finished, we move on to the curtailment period. We send a load shed command, and then we start that same load shift draw pattern. After 4 hours, we send a return to normal command. This equation at the bottom is how we determine the amount of load shifting that was achieved. So we're adding up the energy used during the basic load up portion, plus the difference between the normal period and the curtailment period. And that should all be greater than or equal to half a kilowatt hour. Okay, so since all those words are hard for me to follow, let's look at some data. So let me orient you to what we're looking at here. The blue lines at the bottom here are the flow rate, so the water coming out of the tank. The black is power, and the power scale is on the right side here. You'll see that some of the heating events start with a very large spike and some don't. Don't read anything into that. A heat pump always has an inrush current at the very beginning, and our data acquisition system was collecting it 1 second. So sometimes we caught it and sometimes we didn't. These other lines here are the internal tank temperatures. So red is at the top, the sort of blue teal color is at the bottom, and then the purple is the average across those 6 internal tank temperatures. The other thing on this graph is the shaded regions to indicate portions of the test. So this blue section is the 4-hour normal period. The green is the basic load up. The red is the 4-hour curtailment period. And then the blue again at the end is the normal period. So let's walk through that same test procedure that was described in lots of words on the other screen. So to start off the test, you can see that the tank temperature is lower than the rest of the test because it's been idle for 12 hours. And then we start off by doing a draw and getting heating to start. So heating starts, and now we have a nice 125 degree tank. And then we start the draw profile that is, in this case, a 4-draw cluster. I should mention that the data that's shown here is from an 80-gallon unit, so some of the heating cycles are longer than you might expect with something with like a 50-gallon unit. So the 4-hour period finishes, and the water heater is still heating, so we wait for that to finish. You'll notice that heating did not begin during that first draw at the beginning of the draw pattern. So we need to figure out the volume to initiate heating. So this draw here is a large draw to figure out what that volume is that kicks the heating cycle on. Once that finishes, then we do the draw that's part of the basic load up. This is a draw that is 2 gallons less than the volume of the previous one. And then we send a basic load up command. Can't really tell from this graph, but heating did not begin until the basic load up command was sent. So heating starts, and then once that is finished, we move on to the load shed portion. There's that settling period in between. We send a load shed command and then start that same draw pattern. When the 4-hour window is up, we send a return to normal command, and heating begins. So that is the full basic load up test. The advanced load up test is very similar. The only difference is that we send an advanced load up command instead of a basic. But so the same operation. We start with an idle tank. We do a preheating cycle. We do the load shift draw pattern. After 4 hours, we move on to the advanced load up period. We do that same big draw, minus 2 gallons, and then send the advanced load up command. And then we move on to curtailment. We send a load shed command and do the load shift draw pattern again. And then after 4 hours, send a return to normal command. The equation for calculating the load shift is the same, but because the advanced load up allows the set point to increase, we do expect a larger load shift. And so for the advanced load up case, the load shift should be greater than or equal to 1 kilowatt hour instead of a half. Okay, so data from the same water heater that we saw before. So very similar looking start. We start with the tank that's a little bit cooler. We do a draw to initiate heating. We move on to the draw pattern in the normal portion. Once that 4 hours is up and the heating cycle is complete, we do that same large draw -2 gallons. You'll notice we did not do the big draw to determine the volume because we did this test after the basic load up test. And that's allowed. So if you know the volume from a previous basic load up test, you can use it in the advanced. But if you were just going to skip ahead and not do the basic load up test, you would need to figure out what that volume is in the advanced load up test. So this is that volume that we determined in the previous test, -2 gallons. And in this case, we send the advanced load up command. And you'll notice that the tank temperature goes much higher, up to 140 in this case. Once that heating is complete, we wait our settling time, send a load shed command, and then start the load shift draw pattern. After 4 hours, a return to normal command is sent, but because the top of the tank in this case is still so warm, heating does not start. Okay, so those are the two versions of the load shift test. And then there are 3 other shorter tests that are part of the test method. So the first one is around consumer override. Consumers need some way to opt out of events, and the test explores a couple of different scenarios. So if an event is already occurring, how does a consumer opt out? If a load up or curtailment event is requested while the water heater has already been opted out, does the event start? We would hope not. And then the last case is if a curtailment or a load up event is scheduled in the future, can a consumer opt out in advance? And these are all the different things that this part of the test tests for. Loss of connectivity is another aspect that's very important to understand. If the communication is lost between the water heater and the demand response management service, how does the water heater respond? So there's 2 different scenarios that we looked at for this case as well. Demand response events can be sent either with no end time, with the expectation that a return to normal command would come later, or the event can be sent with an end time. So these are the 2 scenarios that we looked at for loss of connectivity. So if a demand response event is sent with no end time and the communication module loses connection during the event, what does the water heater do? We would expect that after a certain period of time elapses, the water heater should revert to normal operation. In the event that the demand response event is sent with an end time, so let's say it's a 2-hour load shed event, and the connection is lost during that event, we would expect the water heater to complete the demand response event as previously scheduled, since the end time was part of the event definition. And then the last set of tests are around emergency curtailment and grid emergency. So these are sort of escalated versions of load shed. So emergency curtailment allows the heat pump to turn on, but not the backup elements. And then grid emergencies should see no heating at all. So the way this test procedure works is you start a big draw and send emergency curtailment, and you just let the draw keep going. Once the water heater outlet temp gets to 80 degrees F, we send the grid emergency command. And when the water heater outlet temperature drops to 60 F, we stop the draw and send a return to normal command. So even though the tank temperature gets very cold, if it's in emergency curtailment, we would not expect to see anything besides the heat pump running. And then in grid emergency, nothing should be on. And then there are some requirements around messaging. So there are a number of different things that the test procedure asks throughout that the water heater should be sending as data or messaging from the water heater. So operational state is asking about whether the water heater is running or not and in what operating mode it's in. So running normal or idle curtailed or idle elevated. So this returns a statement telling you about what the water heater state is. Current available energy storage capacity is effectively treating the water heater like a thermal battery and asking how much available energy storage is there. So if the water heater is fully heated, we would expect no available energy storage capacity. And then as the water heater cools off or draws take place, that number will get bigger and bigger. The current total energy storage capacity is that sort of full battery value, how much energy can be stored in the water heater total. And then power, how much power is the water heater using at the moment. So in addition to the calculations that are done around load shifts, which we showed on some earlier slides, there's also some calculations done to compare the values that are reported by the water heater relative to the same calculations as done by the ratings lab. So we compare the available energy capacity and the current total energy capacity based on the two sets of measurements there. And then status, the Energy Star product specification and test method are still in draft form, but very close to being finalized. We expect them to be finalized in the next quarter. In the meantime, if you are interested in getting your hands on all the nitty-gritty details I alluded to, they are all available on the Energy Star website shown here. And that's it for my presentation.
Great. Thank you, Bethany. We do have a couple of questions, but as I noted earlier, we will address those questions at the end of all the presentations, time allowing. Our next speaker is Forrest Frizell. Forrest has spent his entire career in the tech industry with leadership roles in government, nonprofit, and utilities. He's a co-founder and CEO of Shifted Energy. Shifted Energy uses machine learning and Internet of Things technology to convert grid-connected devices like water heaters, pool pumps, and batteries into intelligent and controllable demand-side energy assets. He's also the board president for the Purple Maya, I'm not sure I pronounced that right, but Purple Maya Foundation. With Forrest's presentation, we'll take a look at a unique private-public project in Hawaii providing energy efficiency and grid benefits for all stakeholders. Forrest, take it away.
Great. Thank you so much, Bill. It's great to be here. So, aloha, my name is Forrest Frizell. I'm the CEO of Shifted Energy. We are a Hawaii-based technology startup working to advance renewable energy integration through software, data analytics, and smart devices. We were really looking forward to seeing everybody in person. It's been a year of this, and while not there physically, we are excited to connect with everybody virtually today. So for some context, Hawaii has an aggressive renewable energy portfolio standard to be 100% renewable generation by 2045. To that end, government regulations, policy, communities, and industry must align on these goals. And an equitable customer-focused transformation is front and center, especially in an island community where, frankly, we're all neighbors. So Shifted Energy, the utility Hawaiian Electric, and the third-party administrator Hawaii Energy have partnered over the years to provide DER program implementation with grid interactive water heaters and energy efficiency services. And so we've progressed those partnerships to combine both offerings in a delivery model meant to maximize participant energy savings and drive down acquisition costs of recruiting and deployment. The presentation here will focus on a 740-home subdivision located in Waimanalo, Oahu, on the Department of Hawaiian Homelands. This public-private partnership will showcase the foundation of the program and how we got here, and then the potential for generating more customer opportunities, lessons learned, and scale. So in 2018, the Hawaii PUC approved the Hawaiian Electric revised demand response portfolio, and the programs were supposed to be customer focused, and customers would receive compensation for allowing the utility and its demand response partners to control their equipment in order to provide grid services. And the goal was to create a more flexible and reliable grid while at the same time empowering customers with expanded energy options and economic opportunities. So then a year later in 2019, the first grid service purchase agreement went out on the market. And the market format was built for energy aggregators who are treated like an independent power producer with a price per kW purchase agreement. And there were 3 grid services that were part of this program. And so that's load building, load reduction, which Bethany just went over, and then fast frequency response. Now, when people think about renewable energy programs, what often comes to mind is solar, electric vehicles, and home batteries. And so equity and access has been the forefront of the work that we do. And we see water heaters as bridging that gap and that's an ethos of our company and our partners. And as you know, if you've ever been here, Hawaii has a very high cost of living. And it's increasing in Alice households. Alice is asset limited, income constrained, and employed. So essentials such as housing, childcare, food, transportation are all rising faster than the cost of other goods and services. And in Hawaii, and we're seeing this in other locations as well, job growth is concentrated in lower wage jobs. And so there's been minimal increase in wages and fluctuation in job hours. And so schedules and access to benefits makes it harder for workers to budget and plan. And while the numbers of households in poverty has stayed relatively flat from 2007 until 2018, the number of Alice households has continued to increase as the result of higher costs of living and stagnant wages. So how are we solving for all that? For context, here is a quick dive into our grid contract with Hawaiian Electric. And it's a 2.5 megawatt capacity contract that we're profiling today. So we're a subcontractor to OATI, a US-based aggregator. And the key theme that I want you to take away from this is that grid interactive water heaters can be a surprisingly flexible resource that is customer friendly, can address multiple demand response needs at different times of the day using the same resource. And so in Hawaii, our fleet of GIWHs act as a virtual power plant, and they're used to perform grid services, deliverables such as a midday load build to take advantage of rooftop solar, an evening load reduction, and then fast frequency response. And fast frequency response has to be activated in 12 cycles. So these services are stacked, and that means that they are all performed on the same day. And we get paid to manage the capacity and the forecasting. And it's really critical that forecasting is correct because there's only a 10% deviation or we get hit with liquidated damages. I want to go back in time a little bit because it's important for this partnership. And so Hawaiian Electric, Hawaii Energy, and Shifted Energy have been working together since our earliest days. You know, it really does take a village to build an ecosystem of innovation and that exists in Hawaii. And so for some background, Shifted Energy was actually formed out of a nonprofit. And as early as 2011, the three of us were working together to address energy issues in low-income communities. And we saw a need in the marketplace. And so we kicked off our first GIWH pilot with Hawaiian Electric in a 499-unit rental complex. And then 2 years later, in 2018, we partnered it up again. And this time it was to pilot the proposed services as part of this GSPA. And it was the learning from those pilots that benefited all of the stakeholders so that we were really informed and we could shape where we are today. Then, you know, in 2020, as we all know, COVID-19 hit and it forced us to pause and think hyper-local about how could we be doing more. And so we selected Waimanalo because we thought we could build a strong community partnership and then work with Hawaii Energy to combine DER with energy efficiency and offer a full menu of energy saving and bill saving measures. And the goal of the partnership was to drive down customer acquisition and drive up value. And we really thought to move deeper, we have to think bigger. So a little bit about Waimanalo. Half of the town of Waimanalo is made up of land that is classified by the Department of Hawaiian Homelands. And so it's similar to an Indian reservation where benefactors must be of Native Hawaiian descent. But what's different is they own the structure, but they don't own the land. The land is leased in 99-year contracts. And so it makes building equity in the home challenging. So financing home improvements can be really challenging. And we've found that 40% of the homes on Homestead required repair work that couldn't be financed by the benefactor. The median age is 56 years old, and about half of Waimanalo falls well below the HUD medium income. But on the flip side, the town has a ton of pride. 70% of the residents rate it as a great place to live. It's home to a couple of the most innovative charter schools that combine ancestral science and technology, like wayfinding and sailing, to some of the very first Hawaiian language immersion schools. So with outreach and recruiting, the goal was to provide residents and communities the opportunity to save energy and money through multiple program channels. The program consisted of a bill credit for the Grid Interactive Water Heater program, and then energy efficiency through free home energy audits. We call that Energy Smart for Home, and appliance trade-ups. And so we used postcards like this one, word of mouth, a couple social media posts to drive interest. So now let's dig into the fun part, the data. Hawaii had some of the strictest COVID-19 shutdowns in the country, and so it really affected our ability to recruit. We could not do any face-to-face recruiting. There were no events where we could do recruiting, so it made it very difficult. So it was a combination of the mailer you just saw and some social media posts. So 30% of those that connected with us came in through phone calls. 54% used our web form, 4% on email, and then 5% were referrals. And of those, 39% wanted both the energy efficiency and the demand response grid interactive water program. 52% wanted just the demand response program. 84% wanted just the energy efficiency. What was interesting with that is we combined the gas and solar water heating in this number. Oftentimes people don't even know what type of water heater they have. I'm sure people in the crowd have run into that, but we'd get there and, they had a solar water heater and couldn't join the program. And then about 7% ended up declining, and that was almost 100% because of COVID concerns. So we're in the process of developing our evaluation, but customer acquisition costs are front and center here. And anecdotally, we've seen this approach to be more cost effective. A recurring theme across the board was support for the program. We had a lady who made her own copies of our flyer, and she was reaching out on our behalf to her neighbors and her family. It was really pretty cool. And then finally, our lessons learned. So most importantly, you have to make the customer experience simple, meaning stay away from utility speak. For example, we don't say grid interactive water heating or GIWH. We use terms like smart water heater program or smart timer for your water heater. Well, tried to keep our flyers as simple as possible, not too much text, using pictures. The biggest thing is even free is challenging to sell. And I think it's a sign of the times. There's just so much misinformation out in the world right now, and people just don't trust that an offer like this can be free. They're expecting a gotcha at the end. And that's why the community partnerships are really key. You have to build trust. Supply chain coordination is also critical. So an example here, part of our offering was a rebatable appliance swap out. But due to COVID-19 supply chain interruptions, we've had to put that offering into a later phase. And so we're actually looking at probably April for that. And when it comes down to it, people just want face-to-face conversations. And so we put some safety precautions in place to allow for some conversations. And once trust was established, then people wanted to help participate. And in Hawaii, we call that the coconut wireless, and it can happen both ways. It can work both ways, but for us, it's been really positive. So thank you for your time today, and look forward to any of your questions.
Conservation, science, and technology. He's widely recognized for his work in different aspects of building heating, cooling, dehumidification systems, including novel heat exchanger, enhanced phase change processes through the deployment of additive manufacturing, porous media and surface morphology, heat pump and air and water heating, efficient, separate, sensible, and latent cooling systems and emerging refrigerants. He has pioneered the development of new generation of high-temperature heat exchanger manufactured with ceramics and composites using additive manufacturing. More recently, his research has led to the development of unique concepts for direct air capture of carbon dioxide using existing building infrastructure. Today, Kashif will review how adding storage technology can increase load-shifting benefits offered by grid-connected water heaters. Kashif, take it away.
Thanks, Bill. I want to make sure that all of us, we are muted because I can hear some echo. Okay, so that's better. So as Bill noted, I'm going to talk about the heat pump water heaters as a distributed energy storage solutions. So Bill, I don't know, is it just me or can you hear any background? Okay, I guess we are in good shape, so I can move on to the next. I can move on to the next slide. So this is the agenda for today's discussion. I am going to talk about what's the motivation of the project we have been working on. And I'll briefly go through the standalone and the embedded energy storage solutions. Then I'll talk about the two different approaches for the energy storage solutions. And in the end, I'll talk about the challenges and opportunities in this area, followed by some future developments in this sector. So just to give an overview of the motivation for this activity, as we all know, water heating is an important part of our building sector. There's more or less 10% of the energy is used by water heating application in the residential sector, and obviously the percentage is even higher in the commercial side. If you look at different water heating technologies, this has been an active area, and over past several years, there has been a lot of interest in the heat pump water heaters. When we compare the heat pump water heaters with some other technologies, well, upfront cost is obviously quite higher, as you can see in the figure on the left side. However, the payback period obviously justifies the deployment of heat pump water heaters, because obviously you can, within 3 years or so, you can recover the additional cost which is associated with the technology. So again, in many ways, the storage heat pump water heaters, they can be considered as a distributed energy storage solution, because effectively we are storing, depending upon the capacity of the storage tank, a significant amount of water. So that is something which is already exists. So the storage tank is an important component within the overall system, because it establishes the capacity of the device. And I want to briefly talk about this parameter. We call it a first hour rating, which is essentially directly related to the capacity of the system, and it has been used extensively to characterize the overall capacity of the system. There has been a lot of interest in improving the first hour rating of the device, because again, there are obviously obvious needs in order to achieve that. And the goal is really to make a device which can have obviously a higher first hour rating without requiring additional footprints. So in that regard, even as the device it stands, it can be considered as a distributed energy source, provided that we are using a storage tank. Now, I want to briefly talk about this draw pattern. I think Bethany also briefly touched on this. There has been obviously various draw patterns depending upon the type of application we are considering. However, if you consider the standard DOE draw pattern, which is used to establish the uniform energy factor for the device, we can see a standard format for drawing the water from the tank. And you can see that over a period of 24 hours, it's distributed. Most of the heat pump water heaters, they have a backup system in form of the electric resistive heaters, and they are there mainly to provide obviously ancillary power as needed in case if the heat pump system is unable to meet the requirement, then those heaters, they kick in and they provide the additional heating. In terms of COP, we have observed that heat pump water heaters, they obviously have more than 3 COP, but in the case of those electric heaters, the maximum we can achieve under ideal case is 1. So in any case, for the overall operation, if we can reduce the usage of any ancillary heating and really rely on the heat pump system, that can obviously have some significant energy benefits. So the overreaching goal of this activity is really to come up with an energy storage solution where we can use again, more or less the same footprints, but we can enable a higher capacity storage device which can provide us a larger storage capacity without compromising, without requiring additional space. So now I want to briefly talk about the 2 concepts when it comes to the energy storage devices. I think it's very important to understand why they are different and what can be the consequences if we select one versus another. So what you can see on your right-hand side is a standalone energy storage module concept where if I want to use this type of arrangement, then obviously I'll be looking for the engagement of a third-party vendor who can install such a device. And then this device will be acting as a connection between the heat pump and the storage tank. So obviously this has been, I'll call it more like a conventional approach where there has been a lot of developments where people have considered storage tank consisting of PCM, which can be used to store the energy, depending upon the capacity of the material, the volume of this device can be smaller or bigger. What you can see on the left side is, I call it an embedded energy storage concept, where essentially we are using the same volume of the tank, and we are considering how we can deploy the so-called energy storage packets within the tank, and they can obviously lead to a highly compact solution. Both of these options, they functionally, they are great. Again, they can provide us increased in the capacity. However, if you consider the logistics which are involved, the option on the left side, which is embedded energy storage solution, is preferred because, again, I can rely on the OEM to develop a system which will be coming as a package unit, if you will, and it can be installed without engaging an additional vendor to manufacture or to install a dedicated storage device. And also, there are some issues related to the maintenance. If I'm considering a dedicated device, I will obviously be looking at a separate pumping system, which will be required in order to take out the energy from a storage device and bring it to the storage tank. So that's, again, another important issue. And then third, obviously, acceptance of the customer is important, must be considered. The customers, they will prefer the package unit much more compared to, a hybrid or a separate storage tank approach. So this activity is really at the early stage. We have been looking at different options which can be used as an energy storage platform. So first and most important is the different type of materials which can be used for such an application. And if you look at the existing phase change materials which have been considered, we have obviously several options. Each option has its own benefits and merits and demerits. To start with the organic materials, we have materials such as paraffins and fatty acids, which can have a very broad range of melting points. The latent heat is obviously acceptable. It's higher than some of the inorganic materials. One other important constraint is the thermal conductivity, which conventionally has been considered as a major factor. However, it highly depends upon how these materials are deployed. Some of the advantages are related to the chemical stability of these materials. They are compatible. They don't really cause any segregation, and of course, they are less expensive. On the disadvantage side, obviously, these materials, they have a low thermal conductivity. There can be some compatibility issues, and flammability is essentially one of the major demerits. When we look at some of the inorganic materials, we look at the salt hydrates and some metallic solutions, which can have, again, a very broad range of energy storage temperatures. The latent capacity is, again, comparable to what we see in the case of organic materials. One major advantage is a higher thermal conductivity if we consider the metal-based energy storage solutions. And again, if you look at the advantages and disadvantages of these two classes of materials, the things which do stand out is corrosion, for example. That's one of the major issues which can require some specific material deployment requirements. And also, there can be some issues such as hysteresis and the phase change segregation, which make these materials non-ideal for the application. However, obviously, all these issues, there are mitigation strategies which can be deployed. One other important criteria to consider is the deployment strategies. And this table over here just show you an overview of how these materials, they have been deployed in the existing applications. Obviously, when we look at the container approach, or we are trying to embed these materials, there can be deployments such as spherical balls, pouches, boxes have been considered, tubes. Microencapsulation has been deployed, and again, in some cases, we can deploy them as panels or spherical shells. Each type of material, when we look at the specific application where they have been considered, it can vary all the way from very low temperature refrigeration applications to air conditioning, and essentially some of them, they have been considered for the water heating applications as well. But all in all, what I want to convey over here is that, again, there are different type of deployment strategies, and depending upon a specific material and the platform which is being considered, we can select one versus another, and obviously one can be preferred versus the other, and that is something which is we are working on the residential platform, trying to assess which one is going to perform better compared to the other options. So just to highlight some of the opportunities in this area, again, this is a project where we are trying to enhance the distributed energy storage solution. And in the context of materials, there is a broad range of materials which can be used. When it comes to the platform selection, obviously the requirement for a commercial platform can be significantly different than the residential platform. So for example, this embedded solution, which we are considering, is more suitable for residential. Commercial platforms, they're more flexible in terms of cost and deployment, and often the split configuration can be utilized for them. There's a lot of opportunity to optimize the system. We can essentially reduce the capacity of the heat pump if we have obviously an integrated energy storage solution, and we can run it on the time of choice for a longer time in order to store heat energy, which can be provided as needed. There are some consequences in terms of reducing the total charge in the heat pump loop, and which can be enabling development for some low GWP refrigerants. This concept can be considered as a major enabler of resiliency and demand flexibility, which is, again, name of the game these days. And then, obviously, if you think about these deployments, they can have implications beyond water heating. In this activity, obviously, we are considering the heat pump water heaters, but the techniques or the deployments strategies which can be developed they can be used for other applications such as refrigeration as well as air conditioning. Some of the challenges which, again, have to be overcome before these technologies can be deployed at a larger scale, they include the material compatibility, talked about the flammability aspects or the corrosion. So we have to make sure the solutions we are deploying is essentially compatible with the application. We also have to look at what are the FDA requirements. In fact, the very reason, well, maybe one of the reasons for which we use a wrapped-around configuration in heat pump water heater is that we want to have obviously a double wall between the refrigerant and the water. So the same constraints, they also stand for the energy storage materials. They also have to take into account the increase in the capital cost. Even if it's becoming as an embedded solution, there will be some additional material cost and deployment cost. And then obviously the customers, they should be willing to afford this additional cost or additional logistics which comes with this technology. And then of course, the process control is very important because that's how we can essentially establish at what point the heat pump should be turned on and how long it should stay on in order to meet the required capacity goals. So towards the end, I would like to acknowledge our sponsors. This project is sponsored by Building Technologies Office at DOE. And I also want to acknowledge the support and the guidance we are getting from A.O. Smith to essentially enable this project. And like I said, this is, again, a very early stage activity. We are making good progress. And hopefully in the coming years, we will be able to report some more concrete results on it. So on that note, I want to conclude, and I thank everyone for listening.
Great. Thank you, Kashif. We do have a number of questions here, so I'll try and spread the questions out among our different presenters. So give me just a second here to get to the questions. So the first question is for Bethany. And Bethany, the question is there a way to design a hot water system fed by a heat pump water heater so that the heat pump continually runs at a steady state instead of ramping on and off? And might that potentially lead to higher efficiency and energy savings?
I think it'd be tricky to design a heat pump water heater that could run continuously, just because the water heater is, the heat pump runs in response to demand. So without that feedback between, water heater responding to demand, I can't quite think of a way to do that. Unless you had like a buffer, like a tank, I guess, somewhere that you could heat up and continually run to heat. And I don't think that there's quite as much of a problem with the cycling that we see in the water heater as much as you might see in like an HVAC system for a building. And the heat pump water heaters are fairly slow when the heat pump is running. So depending on the demand in the house or building, it could feel like constantly heating, just because it does take longer than a standard electric water heater.
Great, thank you, Bethany. I see my panelists have been on the ball. They've answered many of the questions already. So in the chat, the Q&A, a lot of questions are answered. A couple have just come in that have not yet been answered. And so one of them is for you, Kashif. Let me just get this here. What is the size trade-off between adding physical space for PCM versus just increasing the amount of stored hot water? Have there been any lab tests?
Sure, Bill, that's actually a great question. And that's where I think we have to really do our due diligence, because it really depends upon what type of material we are selecting and how much is the latent heat for that material or the energy storage density. So that's actually the one of the most important parameter which has been considered. We have done some analysis on that, and I can share that information, which basically looks at the fundamental properties of the phase change materials which you are considering, the density, the latent heat, and the heat capacity. And based on that, we can do a good assessment. Like if you are, let's say, exchanging 1 liter of hot water tank with that material, then how much additional capacity you're going to get due to that replacement. So yes, there has been some analysis, and I can share that information.
Great. Kashif, the next question is also for you. And what is your favorite material and why?
Great. Well, we have actually looked at some salt hydrates, which can really, fall well under the temperature range which is needed for the application. The reason we like salt hydrates is there are essentially 2 reasons. First, they have low cost compared to some of the other substitutes. And secondly, we don't have to worry about the flammability aspects, which is obviously inherent characteristics of paraffins. However, as we all know, the salts, when we talk about them, there is a high level of corrosion potential associated with them. So in that regard, we, in fact, do have some solutions where we are considering some encapsulation approaches, which are quite novel. They're not metal-based, and we are expecting that they are going to essentially overcome the corrosion-related issues. So, yeah, that's the simple answer at this stage, but obviously we are going through a very comprehensive exercise of down selection.
Okay, we got time for one more question here, particularly for split system heat pump water heaters where the evaporator unit is separate from the storage tank. And this could be, I guess, to either Bethany or you, Kashif. What kind of performance improvements could be realized by shifting compressor operation to times of higher ambient temperatures?
So I can actually give a little background on this. We actually have done some analysis on looking at the degradation of performance of heat pump water heater when we are looking at different ambient temperatures. And there is obviously, some people report it as a linear trend. We have observed it's a little non-linear, but as obviously you go to a lower ambient temperature, your UEF decreases. So in the context of these commercial systems, if there is a potential to run the heat pump during the time when the ambient temperature is higher, then essentially you're going to see an improvement in your overall performance of the system. But again, the issue becomes, well, if you run it for a longer time, you do need obviously the material to store that if you don't have the capacity. So the 2 options are essentially, one is to increase the capacity of the tank, or second is you can use the approach which I presented over here, like some embedded energy storage solution which can store the energy for later use. Bethany, I don't know if you want to add to that.
Yeah, it's funny because when I first read this, I thought, oh, this is definitely a question that PCMs can help solve. How do you shift the energy use during the day? But it occurs to me that additional controls can also play a role. So it's most of the controls that I was looking at were very focused on demand response. And we also talk about shifting load to when there's more renewable energy available, but you could very much wind up in a nice sweet spot where there's a lot of hot water usage in the morning, and you wait to reheat that tank till the middle of the day when it's both warmer outside and when there's more solar energy available on the grid. So you get kind of a nice combination there, forest degrees, with better efficiency and a better source for that electricity.
Great. Thank you. Thank you, Bethany. I think we're just coming up to the end of our time slot here. So I'd just like to remind everyone to join us for the upcoming session if you have additional questions, and also be sure to fill out your survey questionnaire after you've viewed all your sessions. And with that, I think Lynn, are you still here? Can you take it from here?